Welcome to the deep dive. So today we're doing something a little different. We're moving from the philosophical to the purely mechanical. We are going to rip apart the official repair documentation for some high-end ZF Marine transmissions.
Yes, specifically the 63 IV through the 85 IV series.
Yeah.
And, this isn't just a manual. It's more like a high-level engineering instruction set.
So what's our mission here? What are we trying to pull out of this?
Well, we're extracting the critical nuggets, the
Yeah.
things about precision, chemistry, and diagnostics that you absolutely have to know. We're looking for what turns, simple wrench work into high-stakes engineering.
And what really jumps out right from page one is the complexity hidden inside what just looks like a metal box. I mean, the manual itself warns you. It says, read every single page before you even think about turning a bolt.
It really does.
That tells you right away that we're dealing with systems that have, like, zero margin for error.
Exactly. So let's start with the structure, the anatomy. The strength and the precision, it really begins with the housing itself. We're talking about a two-piece aluminum die-cast assembly.
Aluminum, not steel.
Right. They're not relying on just brute force. They're relying on lightweight, precision-machined aluminum.
So why a two-piece design? I mean, couldn't they just cast it as one solid case?
Well, the precision of die casting is what gives you that tight control over all the internal passages for the hydraulic fluid. But you need that two-piece design to actually assemble it to get the shafts and gears inside.
Yeah.
The key, though, is that the sealing surfaces have to be, well, flawless.
Flawless.
Any deviation, I mean, even a microscopic one, becomes a huge pressure or fluid leak down the road.
Okay, so the housing is the skeleton. What's inside? What's actually driving the boat?
The powertrain. So the core of it is governed by three main shaft assemblies.
Okay.
You've got the input shaft. That's where the engine, the power comes in. And, this is critical, that shaft also holds the reversing clutch pack assembly.
Got it. And the other two?
Then you have your intermediate shafts and the reverse shaft. All of them have to interact perfectly.
And what's conducting that whole orchestra? This isn't a manual shifter, right?
No, it's all hydraulic.
Yeah.
And that's where the control block comes in.
The brain.
The brain of the operation, exactly. It manages the fluid pressure. It decides precisely when and how much pressure to send to the clutch packs, to shift from forward to neutral to reverse. The entire system's integrity hangs on that block, doing its job perfectly.
Before we dive into the hydraulics, I want to go back to some of the simpler parts listed. Things like the oil filter, the dipstick, even the breather valve. Why are these seemingly basic parts so important here?
Because they're the gatekeepers. Take the breather valve. Its job is just to equalize pressure as things heat up and cool down.
Simple enough.
But if it gets clogged with dirt or even paint, the internal pressure can build up and blow right past a critical seal.
And in a marine environment, that's a disaster.
It's a disaster. You either lose your fluid or, even worse, you get water in. So yeah, precision is about the environment inside the box just as much as the gears themselves.
That is the perfect segue to our next topic, the chemistry of reliability. Because when you put this thing back together, you're not just grabbing any old tube of silicone.
Not at all. This is where you separate the professional repair from the amateur one. For just about every screw, they mandate Loctite 243.
A thread locker.
A medium to hard grade one, yeah. It stops anything from backing out under that constant vibration you get on a boat.
Okay, that makes sense for vibration. But the really interesting part is sealing those main housing surfaces we just talked about. Why Loctite 574 specifically? Why not a normal high-temp RTV sealant?
Because Loctite 574 is an anaerobic sealant.
Meaning it cures without air.
Exactly. So when you clamp those two perfectly machined metal halves together, the sealant cures metal to metal. It doesn't form a thick, rubbery gasket like RTV.
So there's no distortion in the joint. It's helping maintain the alignment.
It becomes part of the structure. It's not just a patch.
Yeah.
If you use RTV, you can actually compromise the rigidity needed for that perfect shaft alignment.
Wow. Okay, and what about the shaft seals? I saw another compound listed for those.
Yes. For the dust lips on the shaft seals, they specify Loctite 5910. It's an extra layer of protection against water and grit. Absolutely critical on the output shaft, where bilge water is always a threat.
So that's a three-part chemical protocol just to bolt the box back together.
And that's before we even talk about the fluid inside.
No, automatic transmission fluid, ATF. It's not just lubrication, is it?
No, it's the hydraulic muscle. And the volume is precise. The smaller ZF63 IV takes about 2.4 liters.
Or about 0.6 U.S. gallons.
Right, but the bigger ones, the 80 and 85 series, they take a lot more, 8 liters. over 2 gallons.
And getting that volume right is all about making sure the control block has enough pressure to work the clutches.
It is, and the manual is very, very clear on this. Clutch slippage, one of the worst failures, can be caused by using an inadmissible fluid.
It's the Achilles heel.
Totally. The friction material on those clutch discs is designed specifically for ATF. You put the wrong gear oil in there or fluid with water in it, and you just destroy the friction coefficient.
Which means heat, wear, and eventually no power to the propeller.
A complete failure.
This all brings us to the real crux of this deep dive. The level of surgical precision needed for any of this maintenance. We're talking about specialty tools now. Your standard wrench set isn't going to cut it, is it?
Not even close. You need specialized gauges, mandrels, pullers. They're non-negotiables. But the most important part is having the gauges to measure incredibly small internal clearances.
This is where it gets into high-level engineering, adjusting the bearing clearance or pretension with shims. And to do that, you need a dial indicator. Tell us about the scale we're working with here.
Okay, so we're basically moving into the micron domain. The manual says that the large hand on the dial gauge you have to use measures in increments of 1/100th of a millimeter.
1/100th of a millimeter, that's what, 4/10,000ths of an inch?
It's unbelievably small. We are talking about measurements smaller than a human hair.
So the gauge is incredibly sensitive, but here's what I don't get. The required clearance, the play you're aiming for on the input shaft, is between 0.00 and 0.16 millimeters. Why is that tolerance window so wide? I mean, 0.16 millimeters seems huge compared to the gauge's sensitivity.
That is a fantastic question.
Yeah.
And the answer is you're dealing with cumulative tolerances. You're fighting friction, heat expansion, and the manufacturing limits of the bearings and the shims themselves.
So you can't just dial it into a perfect number.
Exactly. The shims come in specific thicknesses, so you're trying to land inside that window. If you hit 0.05 millimeters, that's great. If you hit 0.16, that is the absolute outer limit before you start getting noise and excessive load on the bearings. That range is the window of reliability.
So it's not the gauge that's imprecise, it's the physical limitations of the parts.
Precisely. And to even get to that point, the assembly itself requires managing temperature.
What do you mean?
To get the inner races of the tapered roller bearings onto the input shaft, you have to heat them
Heat them.
to approximately 120 degrees Celsius. That's 248 Fahrenheit.
So thermal expansion is actually a required step, not just a shortcut.
It's the only way. At room temperature, the hole in the bearing race is actually slightly smaller than the shaft.
It's an interference fit.
A microscopic one, yes. You heat the race, it expands just enough to slide on. Then as it cools, it shrinks and creates this incredibly powerful grip. It guarantees zero movement between the race and the shaft, which is critical for holding those tiny clearances when the engine's at full power.
That is incredible. Okay, let's wrap this up with the diagnostic map. This is the payoff for understanding all that precision. How does the manual connect a symptom you feel on the water to a root cause inside that box?
It lays it out perfectly. Symptom, possible cause, remedy. It turns weird boat behavior into a logical problem.
So give us a classic. Let's say the transmission is dragging in neutral. The prop is still turning slowly when it shouldn't be.
Right. The immediate thought should be, something is touching that shouldn't be. The manual points to a likely cause. An intermediate gear has literally moved sideways off its shaft and is now physically rubbing against the clutch drum.
How does that even happen?
It happens because the needle bearings holding that gear in place have failed, which, goes right back to that initial bearing play we talked about, or contaminated fluid.
What if the transmission just won't shift at all? You move the lever, nothing happens.
Well, you check the simple stuff first. Loose lever, remote control fault. But if those are fine, the critical mechanical cause is a complete lack of shifting pressure.
Which points you right back to the hydraulic system.
Straight back to the control block, the pump, or a major internal leak.
And finally, the marine nightmare. You check your fluid and it looks
Good.
milky.
Water. You've got water in the fluid.
Where's it coming from?
Two main suspects. First, a faulty fluid cooler. That's where engine coolant or raw water can mix with the ATS. Second, and this is common, is if you have a lot of water in your bilge, it can actually be forced past the output shaft seal.
This has been a really comprehensive look at reliability. It's just amazing how the performance of this massive, powerful drive system all comes down to, well, microscopic precision.
It really is.
That choice of Loctite 574 is just as important as setting that bearing play to within 0.16 millimeters.
It connects every single detail. The decision to heat a bearing race to 120 degrees is directly linked to preventing noise or drag years later. This manual just shows that proper maintenance isn't a fight against breakage. It's a fight against tiny, microscopic inaccuracies.
It really makes you rethink what reliability even means. It's not just strong parts. It's parts positioned and secured with 4/10,000ths of an inch precision.
Right. So maybe here's the final thought for you to chew on. What other complex, high-stakes systems are out there in your life? You know, an airplane wing actuator, the hard drive in your computer, all operating completely unseen and unappreciated
Right.
on that same 1/100th of a millimeter tolerance.